An electronic comparator is a device that compares two analog input voltages and provides a digital output voltage indicating which input is higher. The comparator output operates as follows: a high voltage if the non-inverting input is greater than the inverting input, a low voltage if the inverting input is greater than the non-inverting input. A comparator can be implemented using a regular operational amplifier. However, it is often desirable to use a specialist type such as the LM393, which is optimized for comparator operation. The main features of a specialist comparator device are faster switching times, as it is not compensated internally for stable linear operation. Typically has open collector, open drain outputs suitable for driving logic levels directly. Rail-to-rail output due to the open collector, open drain output stage design. The following illustration shows us a simple operation of a comparator using some defined voltage levels. We can see that the non-inverting terminal is at greater potential than the inverting terminal due to the +2 voltage source. This means that the comparator output will be at the 12 volt power supply. This is due to the external 10K pull-up. Now if we reverse the direction of the voltage source between the input terminals, we can now see that the inverting terminal is now at +2 volts greater potential than the non-inverting terminal. This means that the comparator output will be close to 0 volts due to saturation of the open collector output transistor. The saturation of the output transistor is like a closed switch. This means that all of the supply voltage will be dropped across the 10K pull-up, leaving close to 0 volts at the output terminal. The typical comparator configuration looks like the following. A reference voltage is chosen to compare the input signal against. The reference voltage is generally made up by creating a simple resistive divider. However, if precision is required, it is better to use a Zener diode reference as it has better voltage stability and temperature performance. The choice between connecting the reference to the non-inverting or inverting terminal depends on the output polarity required by the design. Connecting the reference to the non-inverting terminal in the following circuit means that when the input is higher than the 6 volt reference, the output will swing low, and when the input is lower than the reference, it will swing high. If we reverse the connections and connect the reference to the inverting terminal, then when the input is higher than the reference, the output will swing high, and when it's lower than the reference, it will swing low. We can observe the ideal operation of a comparator by watching a slow simulated triangular wave increasing and transitioning above and below the reference point. This is displayed on the top input graph shown in green. We can also observe the clean output transitions whenever the triangular wave crosses the reference point. This is shown on the bottom output graph in blue. The comparator input can be connected to a temperature sensor or a light-dependent resistor. In this configuration, the output from the sensors carry a small amount of noise on the signal. This can be observed if we zoom into the millivolt range on the signal and have a look at it on the oscilloscope. The noise is generally an addition of many sources, such as thermal noise, electrical interference, and power supply instability. This can be challenging to remove completely with hardware using filters, etc. The noise can create problems due to the jagged peaks and troughs that occur as the signal is transitioning through the reference level. The noise can also cause erratic transitions on the output, which can create issues for systems where the output is connected directly to a relay or a microcontroller. Relays will chatter, which can shorten their lifespan, and microcontrollers can jump in and out of interrupt routines hundreds of times, which steals valuable processing time from the processor. In the next slide, I'm going to show you how to add hysteresis to the design to ensure smooth level transitions every time. The level of hysteresis can be designed to cater for the level of noise in the system. So let's look at a comparator with hysteresis. Why is hysteresis useful? Hysteresis means that the comparator has two different threshold voltages, one for when the input is rising and another for when it's falling. These are known as the high and low thresholds. This behaviour is achieved using positive feedback, which introduces a small amount of regenerative action. Essentially, it causes the comparator's switching point to shift depending on its current output state. As a result, the input voltage has to move further before the output flips, helping to prevent rapid toggling caused by noise or small fluctuations near the threshold. Why do we use positive feedback? Here is a t-shirt you do not want to wear when doing your comparator designs. Now we have one that's a bit more positive and should get the job done. A comparator drives an operational amplifier into a non-linear binary mode, either high or low with no in-between. By feeding part of the output signal back to the input through a resistor network, we reinforce the current state, helping the output switch faster and more decisively. This feedback not only sharpens the transitions, but also creates the distinct upper and lower thresholds, a key part of hysteresis. In contrast, negative feedback is used to stabilize and linearize circuits, great for amplifiers, but not for comparators. If we use negative feedback here, it would cancel out the hysteresis effect, which is exactly what we want to avoid. So let's discuss the types of comparator hysteresis configurations. We will examine shortly two simple comparator hysteresis configurations using a single power supply. These configurations will show how to design with a non-inverting or inverting output configuration. The scope of the discussion will be limited to single supply designs that have an open collector output and are designed to have a symmetric hysteresis band around the supply voltage midpoint. When designing with other configurations, such as with a dual power supply or push-pull outputs, the fundamental principles discussed remain the same and the logic can be adapted accordingly. I have developed 4 simple steps to follow when designing a comparator with hysteresis circuit that we will further discuss. Step 1. Determine the output polarity requirement. If we want the output to swing high when the input is greater than the reference, then we require a non-inverting hysteresis design. Be careful to ensure the source resistance is low if choosing this configuration. If we want the output to swing low when the input is greater than the reference, then we require an inverting hysteresis design. Step 2. Determine the level of hysteresis required. Determine the level of hysteresis required to overcome the noise observed in the system. Once the level is determined, the high and low thresholds are normally designed symmetrically about the reference voltage. The reference voltage must be chosen to be the midpoint of the supply voltage to produce symmetrical threshold bands. Just to give you an example, if we determine that 1 volt is the level of hysteresis required in the design and our reference is 6 volts from a 12 volt supply, we can graphically observe the thresholds. We can see that V sub high is half a volt above the reference and V sub low is half a volt below the reference. This means that the input needs to travel through both bands for the output to change, which forms a total of 1 volt. Step 3. Choose a suitable comparator integrated circuit. Pay close attention to the following datasheet specifications: single supply range, input common mode voltage range, and input offset voltage. For example, if we look at the datasheet for the Texas Instruments LM393 comparator, we can see that the supply voltage range can operate between 2 to 36 volts. This complies with our 12 volt reference design shown on the left. So you might be wondering what the common mode voltage range specification is, and trust me, it's not as bad as it sounds. It basically defines the allowable voltage range for the non-inverting and inverting terminals relative to ground. From the datasheet snippet below, we can see that the input terminals can go as low as ground, which is great. However, it cannot exceed the supply voltage by V plus minus 2 volts. If we examine our reference circuit on the left, we must ensure that our input voltages do not exceed 12 volts minus 2 volts, which equals 10 volts. Just to give an additional example on this, I once designed a comparator circuit using an LM393 that had a 3.3 volt supply. I set a reference to half of the supply voltage, which was 1.65 volts. Therefore, I exceeded the common mode voltage specification by 350 millivolts, as the reference should have been kept below 1.3 volts. It did not damage the chip, but it did behave like it had little gremlins inside it, with the output swinging low when it should be swinging high, etc. Furthermore, the input offset voltage has a maximum of 9 mV in the datasheet. Therefore, when designing our comparator with hysteresis circuit, we need to ensure that our hysteresis band is greater than this value for the comparator to operate as expected. Step 4. Choose and calculate the resistors. We will now derive the equations for the non-inverting and inverting hysteresis designs so that we can easily calculate the positive feedback resistor value to implement the hysteresis bands. If we are using symmetrical bands around the midpoint of the single supply, then only one formula is required. R sub 3 can be chosen to be any arbitrary value in the low kiloohms range. The formulas that we will derive are very different for the non-inverting and inverting design. So let's further examine both cases. So, starting with the non-inverting hysteresis design. So here we have a simple non-inverting comparator design with 1 volt of hysteresis. When the input signal rises above 6.5 volts, it will cause the output to swing logic high, and when it falls below 5.5 volts, the output will swing logic low. This makes total sense because it's non-inverting. So our first goal is to determine R sub F for the V sub low threshold of the non-inverting design. So we set V sub low equal to V sub in and the non-inverting terminal equal to V sub ref at the transition point. At the transition point, we need to analyze the circuit in its logic high output state. This is because as we approach the switching point, the input signal will be falling and pass through the lower threshold, which causes the output to swing low. If we perform nodal analysis using Kirchhoff's current law at V sub ref, then we can derive the formula we need to calculate the feedback resistor for our predetermined hysteresis band. So let's label the node currents with the red arrows to indicate the direction of current flow. Don't stress if you choose the wrong direction, as it just means the currents will be negative. However, you do need to be consistent defining the non-arrowhead end throughout the equation as the higher potential and the arrowhead end as a lower potential. Okay, so let's start with the arrow on the right hand side. So at higher potential we have V sub S, and at lower potential we have V sub ref. So it's V sub S minus V sub ref divided by the resistance, which is R sub Pu plus R sub F. Then we know from Kirchhoff's current law that whatever goes in must come out. So looking at the arrow on the left hand side, we can say that V sub ref minus V sub low divided by the resistance, which is R sub 3, to give us an expression for the right side of the equation. Now we can rearrange the equation to make R sub F the subject. So if we substitute in the numbers and calculate, this will give us a result of 599 kiloohms. So for our second goal, we want to determine R sub F for the V sub high threshold of the non-inverting design. It should be noted that we want the value of the feedback resistor, R sub F, to come out very close to the previous value, as the purpose of this calculation is to double check our work. Also, if we want to keep a simple circuit design, we obviously want to implement the same value of feedback resistor that works for both output states. So once again, to derive the formula for the V sub high threshold, we set V sub high equal to V sub in and the non-inverting terminal equal to V sub ref at the transition point. At the transition point, we need to analyze the circuit in its logic low output state. This is because as we approach the switching point, the input signal will be rising and pass through the upper threshold, which causes the output to swing high. So performing nodal analysis using Kirchhoff's current law at V sub ref. For the arrow on the left hand side, we have V sub high minus V sub ref divided by R sub 3. And that equals V sub ref minus 0 volts divided by R sub F. So if we rearrange to make R sub F the subject of the equation, Then we'll substitute in the numbers and do the calculation, and this should give us a result of 600 kilo ohms. So now that we have determined all of the resistors in our design, let's observe a graph of a noisy input signal and show how the hysteresis solves the issue of the erratic output transitions that we saw earlier. So let's look at an inverting hysteresis design. So now we have the same simple comparator design as before with 1 volt of hysteresis, but it's an inverting type. When the input signal rises above 6.5 volts, it'll cause the output to swing logic low, and when it falls below 5.5 volts, the output will swing logic high. This makes sense as it's an inverting type. So our first goal is to determine R sub F for the V sub low threshold of the inverting design. When the output is in its logic low state, we can analyze a circuit to determine its low threshold voltage. This is because as we approach the switching point, the input signal will be falling and pass through the lower threshold, which will cause the output to swing high as it's an inverting type. Performing nodal analysis using Kirchhoff's current law at V sub low, it makes sense to draw the arrow down from the 12 volt supply, as that's the highest point of potential in the circuit, and then the current will split at the node. So let's start by deriving the left hand side of the equation, which is the current through R sub 1. So we have V sub S minus V sub low divided by R sub 1, and that'll equal V sub low minus 0 volts divided by R sub 2. So for the current through R sub F, we can see that it flows through the output transistor, which is fully saturated. So that means it flows to ground. So we have V sub low minus 0 volts divided by R sub F. Now if we rearrange the equation and factor out V sub low, then we divide both sides by V sub low to bring to the other side. Now we'll make R sub F the subject of the equation. Then we'll combine the partial fractions. Finally, cancel out the squared values of R sub 1 and then reorganize. Now we can substitute in the numbers and calculate for R sub F to give us a result of 550 kilo ohms. So for our second goal, that's to determine R sub F for the V sub high threshold of the inverting design. When the output is in its logic high state, we can analyze the circuit to determine its high threshold voltage. This is because, as we approach the switching point, the input signal will be rising and pass through the upper threshold, which will cause the output to swing low, as in its inverting type. Now in this configuration, with the comparator output high, we can see it's out of circuit. So we've got two node currents, one through R sub 1 and one through R sub F, and the pull-up resistor flowing into the node R sub 2. So on the left hand side of the equation we have V sub S minus V sub high divided by R sub 1 plus V sub S minus V sub high divided by R sub F plus R sub PU equals V sub high minus 0 volts divided by R sub 2. Now we rearrange the equation and combine the partial fractions. Some more rearranging and then we'll make R sub F the subject of the equation. Let's substitute in the numbers and do the calculation, and we'll find that that gives us a result of 549 kilo ohms. Now let's observe a graph of a noisy input signal and show how the hysteresis solves the issue of the erratic output transitions for an inverting output configuration. Now to summarize step 4, which was to choose and calculate the resistors, we can now see a summary of the 4 sets of equations that we derived. As previously mentioned, if V sub ref is chosen to be at the midpoint of the supply voltage, then we have symmetrical hysteresis bands and only a single V sub high or V sub low formula for the non-inverting or inverting type is required to calculate the feedback resistor. However, if you have a requirement to design with asymmetrical bands, then both formulas are required. So the key takeaways are, the feedback resistor, R sub F, will be the same when V sub ref equals V sub S on 2, which is basically half the supply voltage, and the pull-up resistor and supply to the comparator are tied to V sub S. The pull-up resistor will create a difference between the V sub high and V sub low calculations, but it can be made negligible by making the value 100 times smaller than the rest of the resistors in the design. Now we are going to design and manufacture a small PCB with the inverting hysteresis design that we previously discussed. The input will be designed to be driven by a trim pot. This will allow us to manually adjust the input from 0 volts to the input high threshold at 6.5 volt. When we cross the input high threshold, it will cause the output to transition to logic low. Then as we decrease the trim pot below the 5.5 volt input low threshold, we will observe the output transition to logic high. We will also add a green LED connected to the comparator output that will turn on when the output is logic low and off when logic high. I have added a 100 nanofarad bypass capacitor to the LM393 to stiffen the voltage rail up if we play around with fast switching times. We will tie the second comparator unused inputs to ground as per the datasheet recommendation, as the LM393 used in the design is a dual version by definition. Finally, we will connect the input to a triangle wave and verify on an oscilloscope that the output transitions at the high and low input thresholds. We will also observe the non-inverting input voltage, which will show us an easy way to visually verify the 1 volt hysteresis band due to the switching in of the feedback resistor, which is dependent on the output state. The schematics and PCB layout will be designed using Fusion Electronics by Autodesk. I normally send all my PCB designs to JLC PCB, as they are low cost for good quality PCBs, and their website makes ordering the design nice and simple. It normally only takes a week to receive the PCB design. Once received, I first hand solder on all the small 0603 resistors and capacitors, followed by the larger components, and then I power up and test, and hope that I haven't buggered up such a small and simple design. Okay, so on input 1 on the oscilloscope, which is a yellow channel, we've got the trim pot voltage. On channel 2, which is the pink channel, we've got the reference voltage being monitored at the feedback junction. And on channel 3, the blue channel, we are monitoring the comparator output. And this is an inverting comparator with hysteresis design. So you can see right now, as I move my input, which is being fed in the inverting channel, we're well below the reference, so we can see that the output, the blue channel, is at logic high, so about 12 volts. So as I slowly raise the input, coming up to the lower hysteresis band of 5.5 volts, and we'll notice nothing will happen to the output. But when I cross my reference voltage on the upper hysteresis band, you can see now that the output switch is low, and you can see that the LEDs come on, which is good. And then I can slowly lower back down, and I can even go above and beyond that upper hysteresis band. Nothing happens until my input comes down and crosses the lower hysteresis band of 5.5 volts, where we switch back to logic high, and you can see that the LEDs come off. So you can see that I have to simulate a lot of noise, more than a volt, to get the output to really come on, off, on, off. So that's an unrealistic amount of noise in practice. So you can see how the hysteresis solves the issue with the erratic output switching. So now for the final check, and with the same points being monitored in the circuit as before. The only change is I'm feeding in a triangle wave, which is about 9 volts peak to peak, shifted up by 4.5 volts into the design. Now this is a really good way to check that the window is operating as expected if you don't have a pot in your circuit or an easy way to manually drive the input voltage. So we can see now that as the triangle wave is rising, it crosses the high upper threshold band, and then you can see that the output drops. On the reference, it also goes low through the feedback path, and then as the triangle wave is basically coming down, it'll cross the lower threshold band, and then the reference will, through the feedback resistor, will swing back up a volt, and also the output voltage comes back up to 12 volts. So I can change the time scale here, and you can see how I've got that nice 1 volt window or 1 volt of hysteresis band. So that's a good quick way to verify